Welcome everyone to session 2 of week 2, where we are set to look at different choices for optimizers and loss functions. The objective of this week is that you should understand the strengths and weaknesses of different optimization algorithms and be able to define the meaning of the following terms. Specifically, what is gradient descent and how does the stochastic version differ? How do these methods seek parameters which minimize the loss, and what is meant by a local and global minima? What is a learning rate and how do you choose one? And how can momentum speed up training? Through these definitions, you should have sufficient context to understand what motivated the evolution of different optimization strategies. Where here we will specifically look at gradient descent, stochastic gradient descent or SGD, momentum, RMS prop, and ADAM. And we will discuss the methods in sufficient detail that you may implement them for a simple loss function of two variables, where this will be the goal of the tutorial. Here you will also have the option to augment the MLP that you wrote in session 1, week 1, to instead make stochastic updates with different batch sizes, training on the same brain imaging feature set that we did then. Finally, we will review a range of commonly used loss functions, noting that these don't all work for all tasks. By the end, you should have at least 2 different loss functions at your disposal for each of classification, regression, and semantic segmentation problems. So starting with optimizers, this will be the main focus of the tutorial notebook this week. Before we get started, I'm going to address a possible point of confusion head-on. As we stated in week 1, we define loss functions assuming a single example, and we calculate the partial derivatives initially with respect to this loss. However, we don't typically update on single examples. We generally update relative to the whole dataset or batches of examples, where we assume each example is a noisy sample from some underlying function. Thus, when we estimate the loss for all of these examples, we don't expect it to be the same for all. Accordingly, we're going to consider the average loss, which we term the cost. I'll step in the direction of the gradient of this cost, which we will get by averaging the gradients of losses estimated across batches of examples. So far last week we only discussed implementation of the basic or vanilla gradient descent algorithm, where here we take steps in the direction of greatest decrease of the cost with respect to all of our parameters. In deep learning, this is generally a very high dimensional feature space that we need to traverse. However, as this is very difficult to visualize today, we are going to predominantly only be considering 2 parameters, for example, shown here. Then, to estimate this direction, as we saw in week 1, we need to estimate the partial derivatives of our cost with respect to each of our parameters. The gradient, therefore, is a vector which defines the direction of steepest descent for this entire feature or parameter space. So here, where there are 2 parameters, it's a 2D vector, but if there were n parameters, then the gradient would be n-dimensional. Then, as we saw in the first session of last week, if we are to reach a minimum of our cost, we must take small steps in this direction of steepest descent. And we do this by subtracting the gradient vector or matrix from our parameter array vector or matrix W. We do this repeatedly and stop when we think it's converged, where this is judged as being the point where the magnitude of the gradient is as close as possible to being 0. Here, eta, this little Greek symbol that looks a bit like an N but isn't, represents the learning rate. It controls how big a step is taken in the direction of the gradient. And given that the goal is always just to take a small step in this direction, just a small proportion of the way, eta is always going to be less than 1. How big you set it, however, can be a bit of a challenge, since if it's too small, the algorithm may take so long to converge that the user may think that it's finished when it hasn't. For example, if you make the gradient updates really small, for example 10 to the power minus 6 or smaller, then they will look close to 0 just from that process alone. The danger then is that the user would stop optimization too early. On the other hand, if you make eta too big, and this could be from setting it only as high as 0.1 or 0.01 or smaller for some problems, then in that case you risk taking far too big steps that will oscillate around the minima. To judge whether your learning rate is too big or too small, It can help to plot the loss over epochs and look at the rate of decrease. This cartoon plot here comes from the Stanford course on CNNs, which you can check out from this link. The general heuristic is if the loss shoots upwards, then your learning rate is clearly far too high, and so what is then happening is that it's completely overstepping the convex part of the loss landscape and diverging off entirely. If it's slightly too high, what you might see happen is that it drops really rapidly and then quickly levels off. This might indicate that it's actually oscillating around the minima, bouncing off the, so to speak, walls of the convex part of the function and able to travel further down. On the other hand, if it's too low, then its improvements will be slow and perhaps linear. So what you're looking for is exponential and steady decay, like the red line. Also, one thing to bear in mind going forward is that you don't have to stick with the same learning rate throughout all of your training. You can reduce it manually or get it to reduce by some factor every few epochs. Deep learning frameworks such as PyTorch and TensorFlow will have functions to schedule this for you. For example, see this link. So in this way, it's possible to start high and then gradually decrease the learning rate as you get closer to the minima, and the loss landscape gets steeper perhaps. In this way, you might achieve optimization faster than starting very low and staying with that learning rate the whole time. Having said all that, we are going to look at some optimization schemes that seek to anneal the learning rate for you effectively. So instead, you might choose to use those. Note that while in these slides and in the notebook, you will see simulated simple, smooth loss functions designed to highlight the key ideas, in reality, the loss landscapes for our deep networks are much different. These will not be convex. Rather, they will have lots of local minima and or saddle points, where saddle points are otherwise known as inflections. These are points in the parameter space where locally the loss is lowest, but somewhere else there will be a parameterization which will result in a global minima of the loss. For example, you can see how locally this is the lowest point, it comes back out again, but overall this is the global minima. Whereas an example of a loss landscape for a deep network, here is a 3D visualization of the loss landscape for the VGG, one of the first CNNs, and you can hopefully see that it's very noisy. And the problem is all these little local minima are potential traps where our optimization can get stuck. And we want to be able to avoid them entirely or jump out of them. So this is what motivates stochastic methods, and these stochastic methods form the basis of most schemes used for deep network optimization, since one way to avoid getting permanently stuck is to leverage randomness. Since if we only consider a subset of our data each time, a local minima for one subset may well not be a minima at all for others. So in this way, we can encourage the optimizer to jump clear of these locations. Strictly, stochastic gradient descent refers to estimating the gradient for just one example at a time. However, this can be particularly slow, since given that it is possible to compute gradients across examples in parallel, if we were instead to pass the whole training set at once, optimization would clearly be performed much more efficiently. So a compromise can instead be to take mini batches, so not one, but perhaps 8 or 32 out of thousands. This is what we mean by a mini batch gradient descent. However, in both cases for mini batch or single example SGD, the optimization will be much noisier than running full batch gradient descent, where by batch here I mean the whole dataset. So you can see a cartoon example of what you would expect if you plotted the loss across epochs for these approaches here. For these reasons, it's more common to implement variants of SGD, where in the terminology of PyTorch, SGD means both single example or mini batch gradient descent. And we're going to go through and review the most common ones now. So let's start by looking at momentum in the context of optimization, where to understand this, we need to first address the concept of pathological curvature. So this happens when the loss landscape includes ravine-like structures for example, where the gradient is much bigger in the direction of one parameter or in a subset of parameters than others. For example, in this case, the partial derivative of W1 is much greater than that for W2, since we can see that the loss is changing much more rapidly in this direction. And when this happens, gradient descent tends to get stuck, bouncing from one side to the other of the ravine as shown here. It can be tackled by reducing the learning rate significantly, but then this can also lead to the optimization slowing so dramatically that the user will terminate before reaching the global minima. Therefore, a better way to deal with the problem can be to incorporate more second order type information. Specifically, the second derivative of any function tells us the curvature of the loss landscape at that point, since it is, after all, the rate of change of the gradient. So it's going to tell us whether the loss function is getting steeper and thus heading deeper towards a minima, or whether it's getting less steep and thus levelling off, possibly at a location of pathological curvature. So what we want to do is adjust the updates so as to avoid getting stuck. In other words, if we are approaching a local minima, we want the momentum to carry us through. And if it's the global minima, we want it to slow down and not overshoot. Accordingly, there are optimization strategies such as Newton's optimization, which makes full use of the second derivative, specifically modifying updates by rescaling so as to make updates smaller if the second derivative is larger, providing inertia, and bigger where it is smaller to propel it across local minima. Unfortunately, estimating second derivatives is highly computationally intensive, and so is a big problem for functions with very many parameters, as it's going to require computation of second order partials with respect to every combination of parameters or weights. Another problem with Newton's method is that it can get stuck at saddle points. Momentum-based approaches therefore approximate the behaviour of second-order optimization through accumulating gradients from previous iterations, such that the gradient update for time t plus 1 combines the update from step t with the gradient estimated for this location in the parameter space, where here beta is the parameter weighting the contribution from the previous update, and eta is the learning rate, as before, in this case weighting the contribution from this gradient step. This operation is recursive, so the update will be accumulating gradients from all previous steps, with higher weight given to the most recent ones. This is otherwise known as taking an exponential moving average. For example, let's say that g of t here is the gradient estimate with respect to our current parameters, wt. If we start at t equals 1, where 0 is our initial state, which is initialized as 0, then this means that at time 1, z1 is equal to beta times 0, because z0 is 0, plus the gradient at this location. So z1 is just equal to g0. At the next time point, however, we combine our current gradient estimate, g1, with beta times our previous update, z1, which we already know reduces to g0. So this becomes beta times g0 plus g1. This then continues to accumulate, such that at time 3, we again multiply by beta, which if we multiply all this out, where here this is our expression for z2, then this shows that the current update takes a smaller contribution from g0 than g1, since g0 is multiplied by beta twice, and g1 is multiplied by beta once, and beta, of course, always has to be less than 1 in order to make sure that the contributions from less recent gradients get smaller. Typically, beta is set to 0.9. So how does this help? Well, it means that the components in W1, the direction of steepest descent, end up cancelling each other out as they have opposing directions. So when they get summed, they just negate each other. This therefore just leaves the gradients in W2, which is the direction that we want to travel in. And these are accumulating, so adding up, such that in this way we move faster in this direction. Such that the practical outcome of all of this is that when training with momentum, you can use a higher learning rate than you would have been able to with pure stochastic gradient descent. Where here, if you follow this link, then you'll find a nice intuitive explanation of momentum as an oscillation dampener, while at the same time you can try out their momentum simulator. Incidentally, that website, distill.pub, is generally a great source for machine learning tutorials with clever visualizations. So now we're comfortable with vanilla momentum, let's consider Nesterov momentum. So the idea here is rather than calculating the gradient of the current position, we can instead attempt to forecast what our optimization will need to do going forward by instead calculating the gradient at an approximated new position. Where a much quoted explanation from Geoffrey Hinton's Coursera course on this topic is the following. If standard momentum takes steps in the direction of the blue arrows, first estimating the gradient at the current location in the parameter space, and then making a correction by adding a contribution of gradients accumulated from previous iterations, then Nesterov instead takes a step in the direction of the green arrow, where rather than first estimating the current gradient and then adding the accumulated past gradients, for Nesterov you instead take a big jump in the direction of the accumulated gradients, see here for the brown arrow, and then you estimate the gradient at that point to make a correction, shown in red. So this is written out in notational form, where this part at the end here is telling it to estimate the partial of the loss with respect to the parameters for the values of W at the location in the parameter space given by first updating W with the update of accumulated gradients beta zt. Specifically, stepping forward before estimating the gradient at the new location, as indicated by the vector diagram on the previous slide. Then, the weights for the next step get updated with this combined update step, zt plus 1. It's a bit like allowing the algorithm to anticipate future gradients and thus allowing it to start to slow down before it overshoots. So how do we implement this in PyTorch? Well, actually, you've already seen examples of this in the notebooks, admittedly using traditional momentum rather than Nesterov. So specifically, this was the loss definition from the CNN notebook, and here is the PyTorch documentation. So the required arguments are the network's parameters, the learning rate, and if you want to train with a momentum, the choice of a momentum parameter beta. So by default, momentum is set to 0, but this will then just run straight SGD. So if you want to run with momentum, you have to set the momentum parameter, and a commonly used value, as already stated, is 0.9. If, however, you want to try Nesterov updates instead, you may set Nesterov to true here. Ignore the weight decay argument for now. So next, let's consider RMS prop. This takes a similar approach in that it is accumulating or keeping memory of past gradients, but rather than updating the parameters with a weighted average or accumulated gradient, it uses a moving average of the gradients to update the learning rate on a per parameter basis. Specifically, you can hopefully see here that eta, the learning rate, is normalized through by the square root of v at time t plus 1, with a small adjustment by epsilon to prevent division by 0. V here represents a moving average of the squared gradients, where use of squaring ensures that more recent updates are weighted much more than less recent ones. Accordingly, this expression here returns an array containing learning rate updates for each parameter separately. So this can be used to adjust the gradients for each parameter through element-wise multiplication. The end result is then that smaller steps will be taken in directions with larger gradients. This implicitly performs per parameter learning rate annealing, with the end result of supporting faster convergence, even the momentum, especially for noisy data. However, while applying per parameter learning rate adjustments can speed up optimization, this implementation loses some of the advantages of momentum, which prevent the optimization from bouncing from wall to wall down ravines in the loss landscape. The popular ADAM, or adaptive moment estimation approach, therefore arose as a result of seeking to combine these two types of method. Thus, the learning rate is adjusted by dividing through by the square root of v plus epsilon as before for RMS prop, but in contrast to RMS prop, the update step is a moving average of accumulated gradients like momentum. Note the parameters beta1 and beta2 here are pretty much always set to the following values and do not need to be changed. ADAM does, however, also make another slight adjustment with respect to the previous algorithms, since for these, Z and V are initialized to 0, and this technically means that they're biased towards 0, particularly at the beginning of the optimization. So the ADAM method corrects for this bias by adjusting Z and V in the following way, such that the actual update is as follows. Finally, one quick note about ADAM and RMS prop is that you may find that they do not converge to as good a local minima as SGD, where this recent paper by Reddy et al. Suggests this may be caused by the use of the exponential moving average to update the learning rates, and suggests that it originates from an error in the proof of convergence for the original ADAM paper. So one possible fix is to switch back to SGD with momentum at some point towards the end of training. Alternatively, one can try the correction proposed in the AMS grad paper. However, there was some debate in the community at the time of whether there was a real practical benefit relative to ADAM outside toy problems. Recently, a new technique called ADABAN was also proposed, which observed that perhaps the poor performance occurred mainly for extreme learning rates. So it instead employed a dynamic bound on the evolving learning rates, with the effect of allowing a gradual and smooth transition from initial training with adaptive methods to SGD. In this way, they show comparable accuracy to training SGD with learning rate annealing, but achieve convergence rates comparable to ADAM. A blog on this topic is available here. ADAM remains popular, and if you want to employ ADAM to optimize your PyTorch networks, all you need to do is change your optimizer from the SGD example that we've given you to use ADAM with default betas. As you can see, in their implementation of ADAM, there is an option to use the AMS grad correction if you should want to try it. So that's obviously quite a lot of options. Which one should you choose? If you're not desperately worried about runtimes, then SGD with momentum remains a solid bet. Otherwise, ADAM remains commonly used, and if you're worried that it might be converging too early, you can always switch optimization back to SGD at the end. Alternatively, if you want to try novel optimizers such as AdaBound, you may need to access them via plugin libraries such as the ones linked. The main PyTorch libraries do keep up with research development, but given the sheer volume of options published, not all impactfully, it seems to wait until the methods gain some traction within the community. So, in summary, the goal of optimization is to update the model parameters so as to minimize the cost. We are looking for a specific set of parameters which lead to the best performance of our model, where this is measured by a loss function, and we're going to look at some examples of those in the next video. All approaches to optimize deep networks that I am aware of use variance of gradient descent, which is a first-order optimization algorithm which seeks to update the parameters by taking a step in the direction of the negative gradient, where the step size is controlled by the learning rate eta. The problem is that deep learning involves very high numbers of parameters and the loss landscape is far from convex. And therefore there are a lot of potential local minima or traps that the optimization can get stuck in, which will prevent it from finding the absolute best parameters. For this reason, rather than applying batch gradient descent, deep networks implement stochastic optimizations, where they instead sample a single example or a mini batch. Typically, the size of your batch is going to be determined by the available memory, for which medical imaging is very large, so you're typically going to be dealing with very small batches. However, while in principle SGD allows for optimizations to jump out of local minima, it can nonetheless take a very long time to converge, and if the optimization gets stuck in ravines caused by the situation where for a subset of parameters the loss may be changing more rapidly than others, if the optimization gets very slow, it may appear to have converged, leading to early stopping. Momentum helps address this by instead estimating updates from a moving average of previous ones. This can help to cancel out partials which are oscillating so as to speed up convergence. Further speedups can also be achieved by using adaptive learning rate methods such as RMSProp and ADAM. These are effectively performing per parameter learning rate annealing, where ADAM is specifically seeking to combine the best of both worlds, merging RMSProp and momentum. ADAM remains a very popular optimizer, but it pays to be aware that it has been suggested that it converges too early, perhaps because too many learning rate updates can result in extreme values. So that's it for optimizers. Please attempt the quick Keats quiz before going on to the next lecture on loss functions.